In addition to the time average, the point vector, we can also consider the time average, the energy density. Okay. The time average, the energy density is equal to 1/2 times epsilon E absolute value real E dot D star plus H dot D star. Okay. And now since D is epsilon times E, and epsilon is just a constant, real constant. So E dot D star is nothing but epsilon times E times the absolute square. Okay. And H B is mu H. So H dot B star is equal to mu times H squared. Okay. So we have the time average, the energy density equal to 1/2 epsilon times the absolute square of E plus mu times the absolute square of H. We can further simplify this result by using the result K times E is equal to omega mu H. Okay, we can write this as K times absolute E is equal to omega mu times the absolute value of H. And the K times absolute value of H is equal to omega epsilon times absolute value of E. Okay. So according to this, if we multiply these two equations in this sense, we get K omega epsilon times the absolute square E is equal to K omega mu times absolute value square of H. So we get this identity, epsilon times the absolute square of E is equal to mu times absolute square of H. Okay, so now we have this identity. So these two terms are equal to each other. So we get 1/2 epsilon times the absolute square of E. Okay, so this is the result in the textbook equation 1.4-22。OK， 所以到这边为止，我们把这个平面波啊、单频波、单一频率的波、单色波的这个电磁波的几个主要的结果讲完。好，那现在我再回头来稍微解释一下这个关于单色波的表达方式啊。有些同学可能一开始并不是那么了解，为什么我们单色波的表达方式可以用一个 exponential 什么 omega t 减 k 动的 r 的方式来表示。我再稍微解释一下啊。So now I go back to expand further why we can represent monochromatic wave by an exponential factor times a constant vector. So let me show you that when we consider the simplest wave, a sinusoidal wave, consider a sinusoidal wave, sinusoidal， 我也不知道我拼的对不对啊？你们可能自己琢磨一下，这是英文 ，my spelling might be wrong， you must check the correctness， OK。我们考虑一个单频的正弦波，好，那一个单频正弦波会长什么样子呢？会长这样子，往这个方向传，好，这两点之间距离是 lambda， 对，好 ，a sinusoidal wave looks like this。The distance between two values of the wave is lambda, okay, the wavelength. So, if I want to describe this simple wave, I can write it as, say, the amplitude, instantaneous amplitude is psi. Psi can be represented as, for example, this direction is z. Okay, so psi can be written as. Now I write it in the real function form, not the complex function form. Then I will find how to write it in the complex function form. Okay. The real function form of the wave amplitude, instantaneous wave amplitude, is something like this. This is a constant times psi 1 over lambda times z minus vt. Okay. 2 pi. Okay, 2 pi. So when t is 0, when time t is 0, we get a simple form like this. Like this. So if I increase z by lambda, then we repeat it once. OK， 就是说我现在这个 z 的增加，如果增加一个周长的，增加一个波长的时候，它刚好就 repeat 一次。所以这的确是描述一个这两个间隔是 lambda 的这个情况啊。然后现在如果我把时间打开。When we consider a time different from 0, then I must replace z by a new z so that z minus vt is equal to the original z. Z new minus VT is equal to Z old. Okay, so I see the wave move right hand side. Okay, move toward the right. Okay, then I can write this as like this. So I rename 2 pi over lambda as k, then call it wave number. Wave number. But now what is this quantity? We know that V is just lambda over t. Okay. In one period, propagate one wavelength. Okay. So 2 pi Vt over lambda is equal to this one. However, 2 pi over t is omega. Is omega. Okay. Omega is 2 pi over t. This is the angular frequency. Sometimes we just call omega the frequency without the word angular. Okay, because you know it means angular frequency. If you want the original definition of frequency, just divide it by 2 pi. So now we can rewrite this psi zt as this one. This one. Okay. In fact, we can introduce some different original phase. We can generalize this to say A psi kz minus z0 minus omega t minus t0. Something like this. So originally, so if I take time t0, the position at z0 give us the value 0, then I can generalize this to this. So this can be written as A psi kz minus omega t plus some delta. Here delta is just minus omega t0. Here delta means omega t0 minus kz0, something like this. We can also rewrite the result as remember that sine theta is equal to cosine 1/2 pi minus theta. Okay, so I can write the sine zt as a cosine 1/2 pi minus delta minus plus omega t minus kz. Okay, and write this as a cosine omega t minus kz plus say phi. Here phi means 1/2 pi minus delta. Okay, so we can write the sinusoidal wave as a cosine, like this. Here we encounter omega t minus kz plus some initial phase. Okay, so now I can further generalize this to three-dimensional space. Suppose now we consider the wave propagating along some different direction, say this direction, along the n direction, and along this direction we call this variable zeta. Okay, here is the direction n. Okay, we have the constant phase plan. Here is this plan. This plan represents wave valley. This is another wave valley, and the distance between these two plans is the wavelength lambda. Okay, so in this case, how can we write the similar equation in the 3D space? We can use the idea of projection. So I can write zeta as n dot r. R means the position vector, and this is the position vector, and I may call this S. S is the unit vector along the propagation direction. Unit vector along the propagating direction. Okay. So now I can write psi zeta t as this: a cosine omega t minus k zeta plus phi. Okay, and this can be written as a cosine omega t minus k s dot r plus phi. And we know that we have defined the k times unit vector s as the wave vector. Okay, so combine k and s vector, we get the k vector, the wave vector. So we find that we can write the wave as function of r and t. It is a cosine omega t minus k dot r plus phi. Okay. So at this stage, we can further write this as real part把这叫 AR 好了 ，AR。AR exponential I phi plus omega t minus k dot r. Okay, and this can be further written as real part AC times exponential I omega t minus k dot r. Okay, so now AC in general is AR times exponential I phi. It contains a phase factor. Okay. 所以这就为什么我们在前面，我们一开始我们就说我们这个电磁场可以写成一个 complex vector， 然后写成这个样子。好，那我们现在还可以进一步把它 generalize， 这个变成是 vector。Okay, so we can further generalize this AC to vector, complex vector, and this also corresponds to a vector. Okay, so we can represent monochromatic wave as complex vector field having this phase factor. Okay. 好，这就是我们到目前为止呢讲的这个 monochromatic wave 啊。So this is the so-called monochromatic wave, which means the single frequency wave. So now we consider how to describe a pulse. Pulse. Or wave packet. 我们现在想要描述脉冲或者是波报，好，脉冲或是波报，好。According to Fourier transform， 啊，你们学过的这个傅立叶转换，啊 ，you know that we can write some shape as an integral. We can write something like this. Fx can be written as something like this. Like this. Okay. So we can generalize it to include the time. So we have this result. Here, the omega is function of k. Okay. So now we consider the dispersive medium. A dispersive medium means that we have this function. Omega is function of k. Omega is function of k. But we can have various kinds of relations between omega and k. Not always the simple proportionality between omega and k. In vacuum and in non-dispersive medium, we have in a non-dispersive medium, we always have k proportional to omega, because now we have k is equal to omega times this quantity, and this quantity is frequency independent. So this means that omega is proportional to k. However, in a dispersive medium, in a dispersive medium, we usually have epsilon and mu as function of omega. Omega and mu and epsilon are usually function of omega. So although this relation is still correct, now we do not have this proportionality. We do not have this proportionality, but we still can write omega as function of k. Okay. We still have omega as function of k. So now we consider a pulse propagating inside dispersive medium with a general relation between omega and k. And we see how the wave packet of pulse evolve in time and the space.我们看看这个波包怎么样随着时间演化。好，那这时候呢，这个波包的演化，我们知道什么是波包？What is a wave packet? Before we introduce the idea of wave packet, we usually have learned something called bit. The bit phenomenon comes from the fact that we form a wave function from two plane waves. For example, we have A1 times exponential I K1Z omega t minus K1Z omega 1t minus K1Z plus A2 I omega 2t minus K2Z. Okay. Then suppose we factor out the central frequency and the central wave number. We write omega 1 as omega central omega plus 1/2 delta omega. Okay, and omega 2 as the central omega minus 1/2 delta omega. And K1, K2 are similar. K1 is equal to Kc plus 1/2 delta K. And K2 is Kc minus 1/2 delta K. Okay. So now we can sum them to form the beat. For simplicity, I choose A1 equal to A2 equal to A, for example. Then the psi then the psi z t can be written as A times exponential I omega ct minus kct times exponential I delta omega t minus delta k z plus exponential minus I 1/2 delta omega t minus 1/2 delta k z. Okay. The sum of these two terms becomes cosine A exponential I omega ct minus kct cosine 1/2 delta omega t minus 1/2 delta k z. Okay, so since now suppose the delta omega and the delta k is very small compared to omega 1, 2 and k 1, 2, then this wave has this form: 2a cosine omega ct minus kc z times cosine delta omega t minus this. So the shape is something like this. Something like this. This rapid oscillation corresponds to this part, omega c kc part, okay? And the envelope corresponds to this part, okay? This delta omega delta k part, okay? So if we observe the propagation velocity of the envelope function, we have the phase velocity corresponding to this equal to omega c over kc, okay? And we can define the so-called group velocity as delta omega over delta k through this when we observe how the envelope function propagates, okay? So in a dispersive medium, these two becomes different. different. Okay, so this is called group velocity. Now we generalize this idea from bit to web packet. Which means that in general we can write psi zt as the superposition of many different sinusoidal waves。好，说我们可以用很多个不同的 omega 跟很多个不同的 k 的这种东西，这种平面波去叠加出一个东西出来，那中期就变成一个波包。然后我们再进一步去把它 generalize 成什么呢？积分。积分的时候呢，会是这样子。我们这个 k 的这个 j 的编号就换成是变成是以 k 为变数的函数，什么东西呢？就是说 dk ak exponential I omega of k t minus k z 变成这样 ，OK， so if we consider the continuous superposition of infinitely many plane waves, we get a wave packet from this integral. So in general, we can write the pulse or wave packet as this function psi zt is equal to, it is an integral. We have this is a Fourier transform. This is a Fourier transform. 好，说积分是黎曼河的极限嘛，啊，所以积分其实就是加法，好，这是就加法，原来就是加法。我们有很多不同的 omega， 很多不同的 k， 很多不同对应的系数。去把这些东西加起来变成一个波包。好，那我们现在连续的加，就这个编号就拿掉了，变成积分，啊，就变成积分，好，就变成这样，好。So we have this, wave packet. So you are given this A of k, and you know the dispersion relation omega of k. Omega of k 叫做 dispersion relation. Dispersion relation, which means the definite function form of the omega of k 啊，就这个函数的形式啊，这个 omega 跟 k 的关系叫做 dispersion relation 啊。你给定了这个，然后给定了你要叠加的这些权重啊 ，this can be viewed as weight function. Okay, you can add some k component more and some k component less. Okay, weight function 就是一个权重啊。 函数。它其实还可以带 phase 啊 ，AK can contain some phase factor，OK。然后你这样积分出来，就会得到一个波包啊。就会得到一个波包啊。So usually the resultant sign looks like something like this. Something like this. This is z. Okay. Psi of z 0. 是 z 吧？对，没错，是 z。Okay. And okay, we can plot the absolute value of k like this. K has the peak value around some point k0, and it has the width equal to this. 假如说这个 k 的范围很窄，啊 ，suppose the width of the AK distribution is very narrow, we can get the result approximately be treated as a plane wave. 啊，就是说，如果这个 k 的范围非常窄的话，这叠加出来就跟一个平面波几乎一样。啊 ，so suppose AK is a delta function around k0, we just get a plane wave has k0 as the wave number. OK， 那如果是这个分布很宽的话，我们就会得到一个很窄的这个 wave packet 啊。If we have a wide spread of AK, we will find a wave packet very specific to some position. OK， 好，就是叠出来就会相反，就是好，你们可能学过一个东西，就是说傅立叶转换，一个胖的波包转换变成胖的分布转换变成瘦，瘦的变成胖的，这刚好相反。OK， 比如说你如果去转换一个这个高斯函数啊高选，一个转换之后还是一个高选，但是从一个瘦的变成一个胖的，或从一个胖的变成一个瘦的，啊，就是傅立叶转换跟反转换有这样一个特性。好 ，Now we suppose that we assume that psi zt is real. Suppose psi zt is a real function. Then we must have omega minus k equal to omega k. And 通常还有这样子啦，就是说 a minus k is equal to a star k 啊，就如果 a k 有这个特性 ，omega 有这个特性的话，那这个叠加出来就会是一个实数的函数。好 ，we can obtain a real wave function if omega k has this property together with the property of amplitude, the weight function ak. Okay. So 我们现在要来得到一个近似的表达式。好 ，Now we want to find some approximate expression about the wave packet. Okay. suppose we have a AK like this with not too wide distribution， 不要太宽的 distribution 啊。那因为它不是太宽啊 ，because the useful AK, the distribution of useful AK is not too wide, so we can just expand omega k in the Taylor series around K0。OK， 我们可以在这个 A 在 K0的附近啊，因为我们现在重点是在 K0附近嘛，因为其他地方的 AK 几乎都是0，对不对？所以呢，我们现在有用的 AK 都是在 K0附近，所以这边我们选择的 K 主要也在 K0附近，所以我们就可以做一件事，就是我们可以把 omega k 做泰勒展开，是根据哪一点做泰勒展开？根据 K0去做泰勒展开。We can Taylor expand omega k around the K0 because now only the regions close to K0 is important in the integration。好，所以我们现在就去做这件事，然后来得到一个近似的表达式哈。We can get an approximate representation of the psi zt using this strategy. So now we can Taylor expand omega k as omega k0 plus omega prime k0 times k minus k0 plus 1/2 omega double prime k0 plus k minus k0 square. Okay. For simplicity, we now ignore the order higher than the first order. Okay. Let me assume that only the linear term is important. If higher order term are not important。 什么情况下会是这样呢？就是说，你这个 omega k 这个函数呢，如果在A 在 K0的附近，它的变化非常的平缓，啊，就是不是我们通常需要的高阶项是说它在这附近弯来弯去，啊，弯得很厉害，那我们高阶项就要放进来。但它如果很平缓，就是缓缓增加或者缓缓减少，在 K0附近，那我们就近似用线性去近似它就好了，啊。 So if the omega k function is a smooth function around K0 and varies very slowly comparing to the variation of AK, then we can just approximate omega k by this expansion. 我再给我5分钟，我把这一段先弄一下啊。 So we approximate omega k by this, then psi zt now can be written as exponential I omega k0 t minus k0 z times AK EXP. EXP means exponential. I omega prime k0 times t minus z times k 减 k0 dk. Okay. This is the phase vector corresponding to the k0. Okay, and this weight function is picked at k0, and here we have a function of omega k0 prime t minus z. 那我们现在呢，这个积分呢，我们可以把变数从 k 变成 k 减 k0 啊。Now because dk is equal to dk minus k0, so I can define this k prime, k minus k0 can be defined as a new variable k prime. So this is just a k prime. Okay, now then a becomes a new function of k prime. So the integration integrate through the all possible value of k prime. So finally we get a function of omega prime k0 t minus z. 好，就说我们现在最后的结果会是什么呢？ So the final result looks like this. E to the I omega 0 t minus k0 z times the envelope function of z minus the omega over decay k0 t. OK， 好，那这个是反过来写了，好，就差一个负号而已，好，那这个东西就是这个东西，啊，就是这东西，好，那课本上呢 ，in the textbook k0 has been briefly has been replaced by 0. In the textbook, 0 means k0. OK， 在课本上的0代表的是 k0 的意思。 Here E is not electric field but envelope function. 就这个波包的形状是长这样，这是波包的形状的函数。那波包形状函数里面的变数是什么呢？是 z 减 d omega over dk， 然后乘以 t。So this quantity can be identified as a group velocity. This is the group velocity of this pulse. OK， 好，我们先在这边下课，好，等一下继续。